Okay, let's have a look at the first mechanism that you're taught in year 12, which is the free radical substitution. So this mechanism is a bit stands out a little bit on its own because it only for alkanes that, as we know, they are unreactive. Yeah, so going the wrong direction. So alkanes that they're quite unreactive because there are no dipoles. It's just carbon-carbon bonds and carbon-hydrogen bonds, which are quite strong. So we know that they're not really reactive. Okay, so this mechanism, it just stands out. In fact, we don't really need to know the movement of the arrows, even though it's helpful. So maybe we will revisit that a little bit. So free radical substitution. It's a substitution, which means that overall one element will take the place of another. In this case, an halogen takes the place of a hydrogen. And it involves UV light, which causes the homolytic fissure to form radicals, which are those species with unpaired electrons. In fact, this mechanism always starts with this initiation step, which is a chlorine, and I'm looking over here, chlorine that splits in two chlorine radicals. Okay. In the propagation step, I'm reading here, that is the reaction between a radical and a non-radical to form another radical. So propagation, of course, the radical keeps being formed. And to remember them, I think it's useful to know the basics. So what I mean by the basic is that in every propagation step, there's going to be that product formed. So we can think about, okay, what radical is left behind and so on. So it takes a bit of memory, but then in this way, it doesn't matter how complicated is the initial molecule or which substitution is, we can always work it out. In fact, the first step of propagation is, I'm reading down here, first the radical forms a new bond with hydrogen and leaves a carbon radical. So it always, in this case, the chlorine or any halogen would form the first product of this overall reaction, which is HCl or any hydrogen halide. But this leaves behind the radical on the carbon. This is an intermediate, so it will continue to react, and it always react with the molecule of the halogen. Yeah, and this is what will cause a substitution, reforming the chlorine, which in this case is acting as a catalyst. Mm-hmm. And then we can have the termination step is the cleavage of two radicals. So those two radicals come together to form the actual product that we want. The problem, is that the radicals are highly reactive species. So a lot of side reactions could take place to form mixture of products. So we could have the termination when we have now a bigger alkane. Yeah, or we could have another propagation step, the second one, where it's further substitution. Okay, so it's really difficult to control. What you're required to do here is to write down propagation steps or initiation step or overall, or discuss how suitable this is. Okay, so it's I would say it's more of a, like, not so much of mechanisms, but more of remembering the steps. Okay, mm-hmm. For the curly hour now, we will look at some better examples. Okay, second mechanism to know, electrophilic addition. Okay, electrophilic addition. Before we look at each step that is happening, I wanted to do a bit of analysis of the molecule. In this case, we have an alkene reacting with an halogen. The first analysis is, what is the nucleophile? What is the electrophile? So alkene, we know that it's a double bond, so it's a region of high electron density. So we know that can only react as a nucleophile. So we can think, okay, what about the halogen? How could it react? Well, there is it's a non-polar, of course, because it's just an element. It's just a two of the same atom bonded together. However, we need to remember the induced dipole force, because as soon as the halogen approaches the double bond, it's polarized. Yeah, because of this induced, or a dipole is induced because this region of high electron density would kind of repel the electron density on the bromine. So that's why there is that positive dipole. And this also is what allows the reaction to take place, because this bromine with a positive dipole, looking over here, it's the electrophile. Okay, so we have this polarization taking place. First, curly arrow, nucleophile to electrophile always. Then you have to think, okay, Which one? I mean, the bromine, can it have more than one bond? No, so another bond must break. Okay, in fact, as soon as one new bond is formed, and that's how I want you to think about the curly arrows, it always means a new bond it's formed. So there is a new bond between one of the carbons and the bromine. But this means that the other carbon is left with one electron less than before, because before it was in the double bond and now it's between the bromine and the carbon. And that's why there is a positive charge. The other bromine now, due to this heterolytic fission, has a negative charge. So we have something negative attracted to something positive, always negative to positive. And we have the new bond that is formed. Okay. One very important thing to consider is that the position of the positive charge does matter. So in this case, well, the product doesn't matter because we always have the bromine, but there is something to discuss with this positive charge. Okay. And let's have a look at that. So look at this asymmetric alkene, and this time we have a HBr instead. So HBr, well, it's polar itself, so we know that hydrogen would be the positive dipole and then bromine. The mechanism is always the same, and that's always what I want you to notice. Doesn't matter which one is the electrophile. Every electrophilic addition would be the same mechanism, so that's important. But then, of course, there are a few little things that we need to consider, like the position of the positive charge, because if it's asymmetric and if you're adding an HBr, we could have two different products depending on where the bromine adds or where the hydrogen add. Okay, and we need to distinguish between the minor and the major product. So notice that the major product is the one where the positive charge is in the carbon that it's most substituted. The reason is that we want the most stable intermediate, and the most stable intermediate is the one that has more groups attached that can donate a bit of electron density, and this is called the inductive effect. So the carbocation is stabilized by the inductive effect, which as a definition is the donation of electron density through a bond. And this alkyl group, so every other carbon group, so everything pretty much different than, or carbon groups different than hydrogen, would donate electron density to this carbocation, making it a bit less positive, so more stable, which means that it would be more likely to form. Okay, that's why tertiary carbocations, they're more stable than secondary, more stable than primary. The most stable intermediate is what will determine which one is the major and the minor product. So major is the one with the most stable intermediate. So we can always work it out. But we could also know the rule, and you can remember it pretty much any way you want. For example, in an addition reaction of a hydrogen halide to an asymmetric alkene, the halogen bonds to the most substituted carbon, so in the middle of the chain. Or you can remember it, the hydrogen adds to the less substituted carbon. Okay, that makes sense, but it's important to know these concept of stabilization and donation of electron density. Okay, because we can have a different products. And this is the first curly arrow mechanism that you really come across, so electrophilic addition. Let's now look at another type of mechanism. So we looked at this electrophilic addition. Now let's look at another functional group, haloalkanes. First of all, the analysis always to do is, okay, is there any polarity? Is there any dipole present that would determine, or is there any region of electron density, or less electrons? A bit of general analysis. So a carbon attached to an halogen. Halogens are more electronegative than carbon, so the bond is going to be polar, which means that the carbon is subjected to a nucleophilic attack. So our carbon is always going to be this electrophilic center because it's attached to the halogen, more electronegative. So it's a permanent dipole present in this molecule. Okay, so if we look at the reactions that could take place, we have two important ones to know. Elimination and nucleophilic substitution. In terms of mechanism, I want to focus now on the nucleophilic substitution. To identify the type of mechanism is always to think about what you had as a reactant and what's your product and what's different. In the first one, so you can see we have a functional group, a chlorine, and then we have just a double bond with the removal of one molecule. So we know it must be the elimination. While the other one, we have a nucleophile that has taken the place of the halogen. So it's going to be nucleophilic substitution. But those are two main reactions. Don't worry about that too much for now, because I want you to focus now on the mechanism and the curly arrows. So let's focus on, well, actually, if you look at them, they're all really similar. But let's start with this alkyl one. So notice the movement of the arrows. We have an hydroxide. Hydroxide ion, of course, is negatively charged. So it's going to be our nucleophile that is attracted to the electrophilic center. And as this new bond forms between the hydroxide and the carbon, another bond must break, because carbon can't have more than 4 bonds. So the weakest one will break, which is the one of the chlorine. And in one step, as simple as that, we have this substitution. Nucleophilic, because the nucleophile has substituted into the molecule. Okay? Mechanism of the nitrile, exactly the same. Ammonia, really similar, but there is only one extra step that I want you to notice. And this is because we start with a neutral molecule. So if the nitrogen gives away its pair of electron, nitrogen now has 4 bonds, has formed this dative covalent bond, but this means that it's going to have a positive charge, because it's like it is giving away one of its electrons to the carbon. Okay, that's why we'll have the positive charge. And to identify it, the positive charge, I would suggest first to look at the movement of electrons, so where effectively these electrons have gone, so, and therefore thinking about has it given away extra ones, or has it gained more to form negative, this type of analysis, or thinking about the number of bonds. Nitrogen, we know that it has always 3. So if it has 4, it must have a positive charge, because it must have been a dative covalent bond. So that's the other way to think about it. And because we want this to become neutral, of course, the only other thing that could occur is that the negative chlorine would take away that hydrogen, and the electrons between the nitrogen and the hydrogen go back to it to reform the lone pair of electron. Okay? And this is not nucleophilic substitution to form an amine. Notice that the mechanism, they're always the same. That's why I emphasize so much the nucleophile, electrophile analysis, because that can really help you working out the mechanism. Okay, so I hope it's clear. And in terms of elimination, you don't really need, oh no, I think you need to know it's AQA. So let's analyze it a little bit. So one thing, now that you understand a bit more the curly arrows, is let's go back to this one about the reaction of haloalkanes, because we have the same reagent, sodium hydroxide in ethanol and sodium hydroxide in water. So when sodium hydroxide hits an ethanol, it would react as a base. Base, it's a proton acceptor. That's the key thing. When a hydroxide is in water, it would react as a nucleophile, electron pair donor. So it's actually two very different definitions. Because the mechanism that it would occur, it is different. We saw the nucleophilic substitution, but let's analyze the elimination. So because, as we said, it's a base, it's a proton acceptor, the hydroxide would take away that hydrogen. But if you think about the electrons between the carbon and hydrogen, they have to go somewhere. So they would go into the p orbitals of the 2 carbons. So guess what that forms? A double bond. But of course, because there is a new bond formed between the carbon and the hydrogen, carbon can't have more than 4 bonds. So now it has a double bond here. The weakest one will break, and the weakest one will be the one of the halogen. So these will leave behind an alkene, water, and the halide as well. So in this case, sodium chloride. Okay, so we need to really notice the solvent and think about how would it react, nucleophile or a base. Okay, and this depends a bit on the type of solvent. We don't need to know in details why, but just remembering when it's a nucleophile and when it's going to be a base. Okay. Another important mechanism, reaction, because mechanism, you don't need to know it, but we've recently explained the radical substitution, and this is a really, really similar one that we see with the alkanes, but specifically for chlorofluorocarbons, which are those molecules that are really toxic, that has caused the destroyed the ozone layer. And they stopped the use, of course. There are alternatives now because they realize how harmful they were, but they were harmful because of this mechanism, which is really similar to radical substitution. So the UV light always causes the homolytic fission to form a radical, and normally it's the chlorine that forms the radical. Okay, and the chlorine, it just very reactive intermediate, actually in this case catalyst, that you would react with whatever is present. So in this case, it would react with ozone, which is O3, to form this intermediate. Notice that it's just slightly different compared to the radical substitution because the radical stays on the chlorine, yeah, and releases the oxygen. Okay, but again, we have this intermediate of this chlorine oxygen radical, which would react with another ozone to reform the radical. So notice that we always have an intermediate, and then the catalyst is reformed, and we would have, in this case, other oxygen that overall would form the depletion of the ozone to form oxygen gas. Okay, so chlorine to ozone forms this intermediate, releasing oxygen, and then this intermediate would react further with another ozone molecule to form the catalyst, the chlorine, and releasing more oxygen. So overall, the depletion of ozone.